We're going to talk about inner products. Let's go through the idea of the inner product on a vector space. We are generalizing the concept of dot product to arbitrary vector spaces. That's the idea. There are many inner product spaces that can be defined on a given vector space V. There is also a lot we can do with inner product space that we really can't do on a regular, shall we say, dot product space. So dot product is very limited in what it can do, whereas inner product space now opens up to so much more that we can do a lot of really strange things in those worlds of inner product spaces. Dot product is kind of limited to the basics of, it's very much geometrical, but if you go into inner product space, you can manipulate much more. Notice that when we were doing the other section when it comes to dot product, we never really did anything with P2 space. We never did anything with like calculus. Yeah, we kind of really never went out of our comfort zone in dot product. So when it comes to inner product space, it just means that we can do so much more to it. And when we go to an inner product space, we can look at R to the n, P sub n, and M2 by 2. R to the n, P sub n, M to the 2 by 2 have standard bases. The inner products associated with these standard bases are called standard inner products. And then they can be manipulated in terms of, well, if you have ax squared plus bx plus c, you can put in numbers for the coefficients, and that's all I mean by being manipulated. So there is more that you can do in an inner product space than you can do with just dot product, which is why everything feels like we are using dot product. And in a lot of places, yeah, we are, because they are very much related. It's just that there's more to do and more we can do in an inner product space than in a dot product regular old space, so to speak. Definition of an inner product on a vector space. In the previous section, dot product is a function that assigns the real number u dot v to each pair of vectors u and v in R to the n space. In this section, in an arbitrary vector space V, a function that assigns a real number to each pair of vectors in V has the same property as the dot product in R to the n. Note, a vector space equipped with an inner product is called an inner product space. Along with learning inner product, we have to learn inner product notation. Use new notation. When you see this, notice we're using arrow brackets. Congratulations. Use the arrow brackets. This is signifying inner product notation with vector u, comma, vector v, with each pair of vectors u and v in a vector space V in such a way that the following axioms are satisfied for all vectors u, v, and w in vector space V for all scalars k belonging to the set of real numbers. Here are our 4 axioms. The inner product of u and v is equal to the inner product of v and u. It's a symmetry axiom. It's no big deal. We have the inner product of u plus v, comma, w, is equal to u, comma, w plus v, comma, w, additive axiom. K times u, comma, v is equal to, factor it out, k times u, comma, v. And fourthly, there should be little vector doohickeys there. V, comma, v is greater than or equal to 0. It's a positivity axiom where v and v equals 0 if and only if vector v equals the 0 vector. Let's talk about the definition of norm in this section. Norm is still length, the length or magnitude. The length of a vector u in an inner product space V is defined by the length of u is equal to the square root of the inner product u comma u, and we know it as the square root of u dot u. Seems like nothing's really changed other than the notation, and you're right. Find the norm. Let the given vector belong to the inner product space V. The notation gives it away that we are in inner product space V. If it looks like we're using the vectors from Calc 3, then it's an inner product space. So, we're given vector u is equal to the inner product space point, or vector, -3, 7. According to the definition of inner product space, the setup is the square root of, using the inner product space notation, u comma u vectors. But this is nothing more than using the dot product rule. And so you will end up with -3 squared plus 7 squared, and that gives us the square root of 58. If we are given vector v, which looks like it belongs in R4 or some state, no. If we are given vector v, and again we're in inner product space because of the arrow brackets, all we're going to do is use the definition, which states this is the square root of inner product space v comma v, which is nothing more than the setup of the dot product. And we end up getting the square root of 90, which is 3 root 10. Let's look at the definition of distance in this section. The distance between two vectors u and v in some vector space V is defined by d of arrow brackets uv, the inner product space, and that's equal to the length of vector u minus vector v, which is the square root of u1 minus v1 squared plus u2 minus v2 squared plus dot 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 un minus vn squared. Let's compute the distance between the two given vectors. Using the definition of inner product space, we will get 5 minus a -6 squared plus -4 minus 3 squared. We end up with 11 squared plus a -7 squared, giving us 121 plus 49, and that gives us 170 under the radical. New example. What happens if you're given column vectors? You can go ahead and work straight with them, or you can turn them into vectors. We're going to go ahead and work with them in columns using the definition of inner product space, distance. Plugging them in, we get 3 minus 4 squared plus -1 minus 1 squared plus a -2 minus 5 squared. Squaring them and then adding them all together, we get the square root of 54, which is 3 root 6. Definition of the unit vector in the direction of v. If v is any non-zero vector, then vector u is equal to vector v over the length of v, or again, 1 over the length of v times vector v. Find a unit vector in the same direction as vector v. Vector v is equal to 3, -1, 5. Again, this is denoting inner product space. First thing that we're going to do, take the length of vector v, which looks a lot like the dot product that we know and love from the other section. Simplify, and voila. So step 1, again, always find the length of the vector. Step 2, we're going to use the formula, which is 1 over the length of v times vector v. Whichever format you like, they both mean the same thing. And we are going to put in 1 over, well, we said the length of vector v was the square root of 35. Vector v was 3, -1, 5. Distribute, and call it good. Simplify any radicals if you possibly can. Reduce when you possibly can. That is it. Find a unit vector in the opposite direction of vector v. So here's another vector v. We're now in R2 space. So we got -4, 9. As usual, We are going to find the length of vector v. We're going to square the first plus square the second, add them, call it good, reduce if possible. Second step is to use the formula. In this case, because it is opposite direction, you need that negative there. That'll tell you the opposite direction. Where you put it doesn't really matter. If you want to use it on the length of vector v, or if you want to put it straight into the vector, so long as you put in a negative, it doesn't matter where you put it. I just kind of leave it with the 1 over the length of v and then distribute it, but it really doesn't matter. And when you distribute, you're done. Now again, you can leave it like this unless the directions tell you otherwise, such as to rationalize your denominator. This problem ends up being very interesting. It's not something that we really encounter a lot in linear algebra, but they are kind of fun. The directions are going to say something like, let R2 be equipped with the inner product defined by, and it is defined by this. You've got the inner product, and it is defined by U1 V1 plus U2 V2. Now, the coefficients right now don't really matter to me, but I know this is an R2 space because I'm only given U1 V1 and U2 V2. So, they gave us this. What is this? It's just an R2 space problem. And what they want us to do is find this, this, and this. Let's see if you guys can identify it. But again, this is really just an exercise in inner product space. And we can do a lot more with inner product space than we could with dot product, which is why you find a lot of things that are different in this section. So, find the inner product of U and V. Now this was, again, this was what they defined the inner product space to be. This is basically, for the sake of doing homework anyway, this is the formula that you're going to be using. And what I mean by formula is pretty much the coefficients are going to follow you along everywhere. But overall, this is your equation, so to speak, your format that you're going to follow for this problem. So the inner product is being defined by this, and we're given vector u and v. So we have the inner product of u and v, and what does this mean? Pretty much it is dot product. So we're going to do the dot product of u and v. You got u1 v1, u2 v2. But again, because they defined our R space to be this right here, the coefficients will follow our dot product. So we have 3 and 2 being here. It's the only real new thing. So doing dot product, we're going to multiply and then simplify. And that's pretty much it. The other thing they wanted us to find was the length of vector u. Now it does affect your length of vector u now. So we just put in u1, because this was 3 times the u1 v1 plus 2 times the u2 v2. So it just follows the pattern of what they gave us. And same thing, you're just going to put in your u1, your u2, and use the numbers that they gave you for the formula, so to speak. Multiply, simplify, final answer, square root of 53. Finding the length of b runs the same route as what we did on the length of vector u. You're going to put in the numbers. This is 3 times the u1s plus 2 times the u2s, or in this case, the v1 and the v2. Again, multiply and simplify. Step 4. They want us to find, basically it's the distance. And it is defined as the length of u minus v. Alright, first thing that we want to do. We need to find u minus v first before we find distance of any sort. So we have u1, which was 1, and again this distance, so this is minus, and v1 was a negative 3. U2 is a negative 5, minus v2, which was 2. Going to work it out. And this is what you get when you simplify it. Now, I'm using parentheses just because that was fit in, but it doesn't really matter because this is what's going to go inside the radical. Now look what's going on, okay? When you have, and I want to point this out, before we had, u and v in here, and that's talking about vector u and vector v. In this case, we ended up with u minus v, and so u and minus v goes into both spots because that's the only thing that's going on in here with our vector inner product vector space. So u and v, and I'm just showing you what it would have been if you had two of the same, or just something different over here. That's why I use vector w. So I got u minus v and u minus v. Well, this is u minus v and u minus v. U minus v gave us 4 squared. U minus v gave us 7 squared. Using our formula as well, that follows us through the rest of our little problem. Multiply, add, simplify, and we're done. The thing is, don't forget, since it is a distance, you do need that radical for step 2. Step 1 is crucial. A lot of students just go straight to, they want to put the u minus v in here. You can, it's not advised. It's better to do as a second step, but that's just me. However you do it, as long as you get the right answer, we're good to go. All right, the directions on this one are going to be kind of interesting. But let's see if we can figure out the problem first. Take a look at what we've got for our example for the inner product space of AB. So this is a little formula that they gave us. This is kind of like the inner structure or the inner product structure of, well, looking at the subscripts, that's telling us that we're dealing with a matrix. So without the coefficients, that would be the standard inner product space expansion, so to speak, of a matrix. In this case, looks like it's a 2 by 2. All right. The directions are going to say, let M sub 2, 2 be equipped with the inner product defined by that right there. So my inner product is using this formula. Think of it that way. They gave us A and B in terms of matrices, which makes sense because they gave us A sub 1, 1, dead giveaway. A sub 1, 2, A sub 2, 1, A sub 2, 2. So we knew that was coming. They want us to find, basically dot product, the length, and the distance. Step 1, if we find the inner product of AB, this just means the dot product. Now all of these coefficients in front, such as the 3 and the 2, these all come from the formula, so to speak, of what they gave us. That's where those coefficients come from. So the rest of that, this is basically coming from the matrix. A sub 1, 1, B sub 1, 1, A sub 1, 2, B sub 1, 2, A sub 2, 1, B sub 2, 1, A sub 2, 2, B sub 2, 2. So that comes right off of the matrix. You can string it out if you want, that's fine, but I'm just going to use the matrix because I can follow the pattern that they gave us for the example. And you just simply do the dot product and call it good. The length of A is better known as AA, okay, the inner product of A and A. That's what this is saying, so I really want to get this across because when we start doing something else, I don't want you to freak. So the length of AA is equal to, first off, what does that mean? Remember what the length of AA means. It means that we're going to find the length. The length implies we're doing the square root. The length of A just means the inner product of AA. All right, this is just different notation, but this is kind of what they're following through. Notice I did not put the radical in. You don't have to until the very end, but if you want to, because we are finding the length, you are more than welcome to do it. And then as our final answer, the square root of 4 is 2. The length of B means the inner product of BB. And don't forget, length implies you are doing a square root. And again, it follows the pattern, 3, 1, 2, 1, as far as your coefficients of the given formula, so to speak. Because it's BB, we're going to take the first one squared. So B sub 1, 1, B sub 1, 2, B sub 2, 1, B sub 2, 2. That's part of my radical, not the power. And again, since it is length, take the square root, and you will end up with an answer of 2. So the length of B is 2. Next is the distance of AB. So first thing, you want to find the length of A minus B, since those are both being used. Again, this is part of the formula for the distance. Step 1. All right, A minus B. Remember, there's really no such thing as subtracting matrices. You add the -1 times the matrix. I'm just saying. And I will end up with a final matrix of 1, -1, -1, 0. Now that my matrix is done inside the length, I can then use that to find the distance. So that's going to be my step B, which is the inner product of A minus B, which is now the square root of, and again, the 3, the 1, the 2, 1 come from the formula that they gave us for an M sub 2, 2 space for inner product. And pretty much that's the same thing as you take the A sub 1, A minus B, which is in the A sub 1, 1 spot is 1. In the A minus B matrix, you get a -1, you get a -1, and you get a 0. Again, I'm snaking them throughout, and they also told you via formula which one they want. Multiplying and then adding your like terms, we get the square root of 6. Brand new stuff, but mostly because we're in inner product space and we can do more. That's it. Vector P of x is equal to 1 plus x squared. Vector Q of x, I know it feels weird, is 1 minus x squared. Inner product P and Q has a standard basis, okay, is this. Let P sub 2 be equipped with the given inner product. Now the coefficients on this are 1, 1, and 1 stated in orange. P sub 2, because if you look at it, the subscripts kind of indicate x to the 0, x to the 1, and x to the 2 power. That's kind of what's going on in how they actually state an inner product space for P2. We want to find the inner product of PQ, which is better known as dot product, the length of P, the length of Q, and the distance. So again, P2 has this standard bases, the standard inner product form right here. They can manipulate it and put numbers in front if they so want. So this would be like 3x squared plus 4x, minus 5, whatever they want. But this is standard inner product for P2. Since this was brought up first, I'm going to do this. P was 1 plus x squared and Q was 1 minus x squared. And we are in P2, so something interesting happening here. We are in P2, I have an x squared and an x to the 0 power. P2 means ax squared plus bx plus c from algebra, and notice that P and Q are missing terms. So I'm going to write this in terms of 1 plus 0x plus x squared, and Q in terms of 1 plus 0x minus x squared. The reason I wrote in this order is because the original problem was given in ascending order. The a sub naught, b sub naught is really your x to the 0. And then they went a sub 1, b sub 1 is x to the 1 power. And a squared, a sub 2, b sub 2 is your x squared. So since they wrote the problem in ascending order, I'm going to write our polynomials for p and q in ascending order. So when I want to find the dot product of P and Q, the ones are coming from the formula. The ones in front of the A sub 0, 0, A sub 0 a sub 1 and the a sub 2. So those are where the ones are coming from. And then you just add or subtract like normal, making sure that you have your p sub naught, q sub naught, p sub 1, q sub 1, p sub 2, q sub 2. That's it. Again, that's p sub 1, p sub naught, your p sub 1, that's your p sub 2, coefficient is 1, and you got your q sub 1, or your q sub naught, your q sub 1, and your q sub 2, which is negative 1. I'm just doing the problem in the order it came, so my next thing I'm going to do is the length of p, and as we know, it means I got the square root of p and p. The ones come from our formula that was given, and p we said was 1. All right, that is our x sub naught. Our x to the 1 power did not exist, so that has a coefficient of 0. X squared had a coefficient of 1. Squaring them, adding like terms, we get the square root of 2. Next in line is the length of q, which is qq, which is really the square root of qq. And again, we have our x sub naught, x to the 1, I'm sorry, x to the 0, x to the 1, and x to the 2 coefficients from q, and these are from the formula they gave us for p sub 2. Squaring everybody, adding like terms, we end up getting the square root of 2. Step 4, they wanted us to find the distance from p and q, so this is the square root of p minus q. Remember, we're talking about the length of that. I'll do a different notation just so that it kind of makes sense. First thing you want to do is find p minus q first. So p minus q is nothing more than p minus q polynomials, add or subtract, and then from there to find the true length, all right, you actually take the square root of all that. So in essence, this is like saying now we're doing the length of p minus q now. That's where we're going with this problem. So p minus q is just this. Now we want to find the length of it, which is the square root of p minus q, which is just our answers, 2x squared, 2x squared. Again, I put this in, well in this case I put it in descending order because I ran out of room, but remembering that this is x to the 2, x to the 1, x to the none, and when we plug it into the p minus q formula, keeping in mind the standard inner product they gave us. So one more time, the ones out in front come from the formula that was given. And then I'm going to put our results in here. X to the 0 was 0 coefficient. We didn't have anything when we dealt with p minus q. X to the 1, we had no x to the 1s, so that was a 0. And x squared, our coefficient, remember these are all coefficients, our coefficient was 2. So we have 2 squared. That gives us the square root of 4, which is 2.